All right, let's go. Number 10. The Ep-R paradox. In the spring of 1935, Albert Einstein was not hunting for a new phenomenon. He was trying to win an old argument. Since the 1927 Solvay conference, he had been sparring with Niels Bohr, searching for a thought experiment that would expose quantum mechanics as incomplete rather than wrong. He recruited two junior colleagues at the Institute for Advanced Study in Princeton, Boris Podolsky and Nathan Rosen. The standard model of the time was clear. A particle has no definite position until measured. The uncertainty principle forbids sharp simultaneous values for position and momentum. Not because our instruments are crude, because the values do not exist. Einstein accepted the mathematics completely. He rejected what it implied about reality. Then, the three of them built a scenario the theory could not comfortably survive. Take two particles that interacted once, then separated. Measure the position of particle A, and you know the position of B without touching it. Measure the momentum of A instead, and you know the momentum of B. Either both quantities were real all along, or B changes because of something done far away. The paper is titled, "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" Physical Review, Volume 47, page 777, published on the 15th of May 1935, Bohr abandoned his other work and replied in the same journal, under the identical title, Volume 48, page 696, that October. Einstein's famous German phrase, "Spukhafte Fernwirkung," spooky action at a distance, does not appear in the paper at all. He wrote it in a private letter to Max Born 12 years later. Every escape route was tried. Hidden variables, the particles carried the answers with them from the start, and quantum mechanics simply cannot see them. John von Neumann had supposedly proved that impossible in his 1932 textbook. Great Hermann found the flaw in von Neumann's proof in 1935, and the physics community ignored her for 30 years. Bohr argued the two particles were a single indivisible system, and the question itself was malformed, a position many physicists found closer to a refusal than an answer. David Bohm rebuilt quantum mechanics with hidden variables in 1952 and made it work, but only by making the influence between particles explicitly instantaneous. The problem was not solved. It was relocated. If Einstein was right, the atoms in your left hand and the atoms in a rock on Mars share a description that no distance can separate. Einstein believed he had found a flaw in the theory. What if he had actually found a feature of the world? 29 years passed before anyone found a way to test it. Number 9. Bell's Inequality. John Stuart Bell was a particle physicist at CERN. Entanglement was not his job. In 1963, he took a year of unpaid leave, traveled to Stanford, Wisconsin, and Brandeis, and used the time to work on something his colleagues considered philosophy rather than physics. He wanted to understand why von Neumann's impossibility proof felt wrong to him. The assumption everyone shared was called local realism, and it has two parts. Realism, particles have definite properties before measurement. Locality, nothing influences anything else faster than light. These two ideas underpin essentially all of classical physics, all of engineering, and all of ordinary human intuition about objects. Bell did something nobody had done in 29 years of argument. He turned the philosophy into arithmetic. He showed that if local realism holds, correlations between measurements on separated particles must obey a strict numerical ceiling. Quantum mechanics predicts violations of that ceiling. The paper is On the Einstein-Podolsky-Rosen Paradox, published in 1964 in Physics Physique Physica, Volume 1, pages 195 to 200. Bell chose that obscure journal specifically because it charged no page fees, and he wanted to donate the fee money elsewhere. The journal folded after 4 years. In 1969, John Clauser, Michael Horn, Abner Shimoni, and Richard Holt converted Bell's abstract inequality into a testable laboratory version in Physical Review Letters, Volume 23, page 880. Then came the experiments, and then came the objections. Stuart Friedman and John Clauser measured polarization correlations in an atomic cascade of calcium at Berkeley, Physical Review Letters, Volume 28, page 938, April 1972. Quantum Mechanics 1. Critics answered that the detectors caught too few photons, and the sample might be unrepresentative. That is the detection loophole. Elaine Aspect, Jean Dalibard and Gerard Rogers switched the analyzer settings while the photons were in flight. In Physical Review Letters, Volume 49, page 1804, 1982, Quantum Mechanics 1 again. Critics answered that the switching was periodic and therefore predictable. That is the locality loophole. Each fix produced a new objection. Nobody ever produced a local realistic model that matched the data. Every measurement instrument you have ever trusted assumes that the thing being measured had a value before you looked. Bell proved that assumption is testable. And then, it failed the test. If the world is not locally real, what exactly is it that your eyes are reporting? It took another 5 decades to close the last of the escape routes. Number 8. The loophole-free confirmations. Ronald Hansen's group at Delft University of Technology was building quantum network hardware. Their goal was engineering, entangling electron spins in nitrogen vacancy centers in diamond, well enough to distribute over a campus as a step toward a working quantum internet. Testing the foundations of reality was a side effect of having built a good enough machine. Every previous Bell test had left a door open. 3 doors, specifically the detection loophole, not enough particles caught. The locality loophole, the 2 measurement stations were not separated far enough for light-speed communication to be ruled out. And the freedom of choice loophole, some unknown common cause in the past, could have secretly correlated both the source and the choice of measurement setting. In 2015, all 3 doors closed within months of each other. Bass Henson, Ronald Hansen and 16 colleagues published in Nature, Volume 526, pages 682 to 686, October 2015, electron spins separated by 1.3 kilometers across the Delft campus, with an event-ready scheme and a state fidelity of 0.92 plus or minus 0.03. In December, Lyndon Shalm's team at NIST published in Physical Review Letters, Volume 115, page 250402. And Marissa Justina's Vienna team published in the same volume at page 250401. 3 independent platforms. Same verdict. Then, the 3rd loophole was attacked from an absurd direction. In 2018, Dominic Rausch, Anton Zeilinger, David Kaiser, Alan Guth and colleagues used telescopes at the Roque de los Muchachos Observatory on La Palma to set their detectors using the color of photons from 2 quasars, one emitted 7.8 billion years ago, the other 12.2 billion. Physical Review Letters, Volume 121, page 080403. Violation by 9.3 standard deviations. Any conspiracy arranging those settings would have to have been set up across 96% of the spacetime volume of the past light cone of the experiment. One escape remains, and it is not an experimental one. Superdeterminism, the idea that the universe fixed the experimenter's choices in advance. To test that, the Big Bell test in 2018 recruited more than 100. 000 human volunteers generating random bits for 12 laboratories on 5 continents. Nature, Volume 557, page 212. The violations held. Aspect, Clauser and Zeilinger received the 2022 Nobel Prize in Physics. Superdeterminism cannot be disproved, because it also predicts that you would fail to disprove it. This includes your decision to keep watching this. At what point does an unfalsifiable escape route stop being physics? The correlations are real. What they refuse to carry is stranger still. Number 7. The no communication theorem. In 1982, Nick Herbert was an independent physicist working outside the academy, and he thought he had found a way to send a signal faster than light. His scheme used an entangled photon pair and a laser gain tube to make copies of one photon, then read the statistics of those copies to detect what the distant partner had been measured against. He submitted it to Foundations of Physics. Standard quantum mechanics says entangled particles are perfectly correlated instantly at any separation. It also says relativity forbids information traveling faster than light. Both statements had been asserted for 50 years. Nobody had proven they were compatible. Asher Perez was one of the referees. He recommended publication despite knowing the proposal was wrong, on the reasoning that finding the specific error would teach the field something. The paper appeared as Flash, a superluminal communicator based upon a new kind of quantum measurement, Foundations of Physics, Volume 12, page 1171, 1982. Perez was right. Within months, William Wooters and Wojciech Zurek published in Nature, Volume 299, pages 802 to 803, October 1982, and Dennis Dieks published independently in Physics Letters A, Volume 92, page 271. Both proved the same thing. An arbitrary unknown quantum state cannot be perfectly copied. The no-cloning theorem exists because someone tried to break relativity and failed in an instructive way. Every proposed workaround has died the same death. Amplify the photon instead of cloning it, spontaneous emission injects random polarization and destroys the signal. Use many pairs and read the statistics. The marginal distribution on your side is exactly identical no matter what the distant experimenter chose. Use a weak measurement to peak without collapsing. The disturbance is smaller and the information is proportionally smaller, and the product is fixed. Philippe Eberhard, and later Gherardi, Ramini, and Weber proved it in general form. The reduced density matrix at your detector is independent of everything done at theirs. The correlation is instantaneous and perfect, and it is censored so precisely that you cannot extract a single bit from it. What kind of universe enforces a rule this exact and never explains what it is protecting? The censorship holds even when the particles have no shared history at all. Number 6. Entanglement swapping. John Wei-Pon was a doctoral student in Anton Zeilinger's group in Innsbruck in the late 1990s. The group was working on practical quantum communication protocols, following up on the teleportation experiment they had published in Nature, volume 390, page 575, in 1997. A theoretical proposal by Marek Yukowski from 1993 suggested something the group decided to test almost as a technical exercise. Entanglement, as everyone understood it, required contact. Two particles become entangled by interacting, or by being created together from a single event. The shared history is what makes the correlation. This is the intuitive picture that makes entanglement feel almost reasonable, like two gloves packed in separate boxes. The team made two independent entangled pairs, photon 1 with photon 2, photon 3 with photon 4. Then they performed a joint Bell state measurement on photons 2 and 3. Photons 1 and 4 came out entangled. They had never met. They had never shared a source. The paper is Experimental Entanglement Swapping, Entangling Photons That Never Interacted, by John Wei-Pon, Dick Baumeister, Harold Weinfurter, and Anton Zeilinger, Physical Review Letters, Volume 80, page 3891, published the 4th of May, 1998. The abstract states it plainly. Entangled particles need neither a common source nor a shared past. The glove analogy dies here, and everything built on it dies with it. Common cause in the past, eliminated by construction, since the pairs came from separate events. Hidden signal passed during the Bell measurement. The measurement acts on photons 2 and 3, not on 1 and 4, and the no communication theorem still applies. Coincidence in post-selection, addressed by Kaltenbeck and colleagues using fully independent synchronized sources. Distance dependence. Herbst and Zeilinger's group teleported entanglement 143 kilometers between La Palma and Tenerife in 2015, and China's Mesius satellite distributed entangled pairs over 1,200 kilometers in 2017. The correlation is not a memory of contact. It is something that can be created between two objects retroactively, by acting on two entirely different objects. If entanglement does not require a shared past, what exactly is the relationship made of? And the moment you measure it, something happens that nobody can describe. Number 5. The decoherence problem. Wojciech Zurek was not trying to solve the measurement problem. In the late 1970s, he was working on the practical question of why laboratory instruments always display definite readings. why a pointer on a dial points somewhere specific instead of at a superposition of angles. He wanted to know which basis nature picks, and why. Quantum mechanics has two rules that do not fit together. The Schrödinger equation, which evolves states smoothly, deterministically, and reversibly, and the measurement postulate, which collapses states abruptly, randomly, and irreversibly. Nothing in the theory specifies when the first rule stops and the second begins. Zurich showed that a system coupled to its environment leaks correlations into that environment almost instantly, and that this process selects a preferred set of stable states. Superpositions do not vanish. They spread. The interference terms become inaccessible rather than absent. The founding paper is Pointer Basis of Quantum Apparatus, Into What Mixture Does the Wave Packet Collapse? Physical Review D, Volume 24, page 1516, 1981. Eric Juice and Dieter Zeh followed with the environmental decoherence calculation in Zeitschrift for Physik B, Volume 59, page 223, 1985. Zurich's comprehensive review appeared in Reviews of Modern Physics, Volume 75, page 715, in 2003. For a dust grain in air, the calculated decoherence time is roughly 10 to the minus 31 seconds. For 20 years, decoherence was widely presented as the answer. Then Stephen Adler published Why Decoherence Has Not Solved the Measurement Problem in Studies in History and Philosophy of Modern Physics, Volume 34, page 135, in 2003. The argument is simple and has never been refuted. Decoherence explains why you do not see interference. It does not explain why you see one outcome. The final state is still a superposition of all possible outcomes, now merely entangled with the environment. Objective collapse models, Gherardi-Rimini-Weber, and Penrose's gravitational proposal add a genuine collapse mechanism, but they modify quantum mechanics rather than interpret it. And no experiment has yet detected the modification. The transition from many possible versions of a moment to the single one you are living through has no equation. Why is there only one of you reading this? Some physicists answered that question by denying its premise. Number 4. The many-world split. Hugh Everett III was a graduate student at Princeton under John Wheeler in the mid-1950s. He was not attempting to found an interpretation of quantum mechanics. He was trying to write a doctoral thesis that took the Schrödinger equation seriously without adding anything to it, because adding the collapse postulate struck him as arbitrary. The Copenhagen interpretation, dominant then and still taught first now, says the wave function represents knowledge and collapses upon measurement. Everett asked the obvious follow-up question. If the observer is made of atoms, and atoms obey the Schrödinger equation, what governs the observer's collapse? His answer was to delete the collapse entirely. The superposition never resolves. The observer becomes entangled with it and splits into branches, each of which perceives a single definite outcome and has no access to the others. The paper is Relative State Formulation of Quantum Mechanics, Reviews of Modern Physics, Volume 29, page 454, 1957. Bohr's Circle in Copenhagen dismissed it. Everett visited Copenhagen in 1959 and later described the trip as a failure. He left academic physics entirely for defense analysis at the Weapons Systems Evaluation Group and died in 1982 at the age of 51. Bryce DeWitt revived and renamed the idea in Physics Today in 1970. The dispute has resisted 70 years of attempted resolution. Many worlds cannot explain probability. If every outcome occurs, why does the Born rule assign different weights to branches that all happen? David Deutsch and David Wallace derived it from decision theory. Critics call the derivation circular. Copenhagen cannot say what counts as a measurement. Then, in 2018, Daniela Fratiger and Renato Renner published in Nature Communications, Volume 9, Article 3711, a Wigner's friend scenario in which agents reasoning correctly with quantum theory reach contradictory conclusions. In 2019, Massimiliano Prietti and Alessandro Federizi's group at Heriot-Watt ran a 6-photon version. Science Advances, Volume 5, Article EAW 9832. Two observers recorded facts that could not both be true. In 2020, Nora Tischler, Howard Wiseman, and colleagues sharpened it into a formal no-go theorem in Nature Physics, Volume 16, page 1199. At least one of your basic assumptions about facts, choices, or a single shared world is false. Physics cannot yet tell you which one. If observers cannot agree on what happened, whose version is the record? The strangeness stops being abstract when biology gets involved. Number 3. Quantum effects in living systems. Graham Fleming's group at Berkeley was studying energy transfer in photosynthesis using two-dimensional electronic spectroscopy. This was a mapping exercise. They wanted the energy levels and couplings inside a bacterial light harvesting protein, the Fenner-Matthews-Olsen complex, which acts as a wire connecting the antenna to the reaction center in green sulfur bacteria. Textbook models describe this transfer as hopping. Excitation lands on one pigment molecule, then jumps to the next, semi-classically, losing efficiency at each step. Warm, wet, noisy environments are supposed to destroy quantum coherence in femtoseconds. Biology was assumed to be the least quantum place in nature. The data showed sustained oscillations. Quantum beats between excitons, persisting for up to 660 femtoseconds, far longer than theory allowed. Gregory Engel, Tessa Calhoun, Elizabeth Reed, Tae-Kyu Ahn, Tom Manal, Yuan-Chun Cheng, Robert Blankenship, and Graham Fleming published it in Nature, volume 446, pages 782 to 786, on the 12th of April 2007, using the FMO complex of chlorobium tepidum at 77 Kelvin. Git Penichayan-Kuhn's group reported coherence at physiological temperature in NAS, volume 107, page 12766, in 2010. The field then turned on itself, which is what makes it worth telling. Skeptics argued the beats came from vibrational motion of the protein, not electronic coherence, and a series of papers after 2017 substantially supported that reinterpretation. The clean quantum computer in a Leaf story did not survive, but the harder claim did not die. In 2021, Jingjing Xu, Henrik Moritzen, Peter Hoare, and colleagues at Oldenburg and Oxford showed that cryptochrome 4 from the night migratory European robin is magnetically sensitive in vitro through 4 successive flavin-tryptophan radical pairs. And more sensitive than the same protein from chickens and pigeons? Nature, volume 594, pages 535 to 540. Meanwhile, Mika Salam's group at Alto entangled 2 vibrating aluminium drumheads, each containing roughly 10 to the 12th atoms, in Nature, volume 556, page 478, 2018. In 2021, a NIST team led by John Teufel directly observed entanglement between 2 drumheads weighing 70 picograms each, in Science, volume 372, page 622. Objects heavy enough to see under a microscope have been placed in entangled states. There is no known upper limit. Where exactly does the quantum world end and your body begin? The next answer proposes that the two were never separate categories. Number 2. ER equals EPR. Juan Maldacena at the Institute for Advanced Study and Leonard Susskind at Stanford were not trying to explain entanglement. They were trying to survive a crisis. In 2012, Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully had published the firewall paradox, an argument that black hole evaporation, quantum mechanics, and general relativity cannot all be simultaneously true, and that an infalling observer might be incinerated at the horizon rather than crossing it peacefully. General relativity and quantum mechanics were treated as separate problems with separate mathematics. Wormholes, Einstein-Rosen bridges from a 1935 paper were geometry. Entanglement from a different 1935 paper by 3 overlapping authors was information. Nobody had proposed they were the same object. Maldacena and Susskind proposed exactly that. 2 maximally entangled black holes are connected by a wormhole. And then they went further. Perhaps every entangled pair is, including 2 entangled electrons. The paper is Cool Horizons for Entangled Black Holes, Fortschritte der Physik, volume 61, pages 781 to 811, submitted the 3rd of June 2013. In it they speculate that even the simple singlet state of 2 spins is joined by a bridge of this kind. a highly quantum object with no established independent definition. The conjecture has survived a decade without being either proved or killed. The obvious test, send a signal through the wormhole, fails. Because these bridges are non-traversable, the two mouths recede faster than anything can cross. Ning Bao, Jason Pollock, and Grant Remman showed in the Journal of High Energy Physics in 2015 that detecting the wormhole runs into the same no-signaling wall that blocks superluminal messaging. Susskind himself published Entanglement is Not Enough in Fortschritt der Physik, volume 64, page 49, in 2016, arguing that entanglement alone fails to reproduce the growing interior of a black hole, and that computational complexity must also be involved. Ping Gao, Daniel Jafferis, and Aaron Wall found a traversable version in 2017, but only by coupling the two sides, which means no superluminal shortcut. The particles in your body that are entangled with distant particles would, under this conjecture, be joined to them by geometry you cannot enter. If space is what entanglement looks like from outside, what is a distance actually measuring? One physicist took that question to its endpoint. Number 1. Spacetime made of entanglement. Mark van Ramsdonk at the University of British Columbia was working within the ADS/CFT correspondence, Maldaceno's 1997 result that a theory of gravity in a volume can be exactly equivalent to a theory without gravity on its boundary. Van Ramsdonk was doing a technical calculation. He wanted to know what happens on the gravity side when you reduce the entanglement between two halves of the boundary theory. Spacetime, in every formulation from Newton to Einstein, is the stage. Things happen in it. Entanglement is one of the things that happens. General relativity makes spacetime dynamic and curved, but it remains the arena, and it remains fundamental. Van Ramsdonk found that as he dialed the boundary entanglement towards zero, the two regions of spacetime pulled apart and pinched off from each other. Reduce the entanglement, and the geometry connecting them stops existing. His essay, Building Up Spacetime with Quantum Entanglement, General Relativity and Gravitation, Volume 42, pages 2323 to 2329, won first award in the 2010 Gravity Research Foundation Essay Competition. It builds on Shinsei Ryu and Tadashi Takayanagi's formula relating entanglement entropy to the area of a minimal surface in the Bulk Physical Review Letters, Volume 96, Article 191602-2006, in 2014, Thomas Faulkner, Monica Guica, Thomas Hartman. Robert Myers and Van Ramsdonk derived the linearized Einstein field equations from the entanglement structure of the boundary theory in the Journal of High Energy Physics. Gravity, in these results, is not a fundamental force. It is what entanglement does at large scales. And here is where it stalls. Every one of these derivations is proved in anti-de Sitter space, which has a negative cosmological constant. Our universe has a positive one. No fully worked de Sitter version exists. Attempts to define holography for our actual spacetime have run for over 20 years without a consensus formulation. The result is either the deepest insight in modern physics or a beautiful theorem about a universe nobody lives in. The distance between you and the screen may not be a container. It may be a measure of how correlated you and the screen already are. If space is woven from entanglement, what is the thread hanging in? None of these entries sits at the frontier of physics. Every one of them sits at the center, inside the most tested, most confirmed. Most technologically productive theory human beings have ever written. Quantum mechanics has never made a wrong prediction. That is precisely the problem. A theory that fails tells you where to look next. A theory that succeeds perfectly while remaining unintelligible tells you something worse, that the universe is not confused about what it is doing. We are. And it has been patiently returning the correct answer to every question we knew how to ask, while refusing every question we actually wanted answered. If you want to see more videos like this, click the video on screen now.